Okay, this is, at least currently, question 7 in the Systems of DE's homework. Kind of a challenging one, at least this particular version. Remember, everybody's probably going to get a different version of this problem, but this particular version, something weird happened. We end up getting 0 for one of our C's at the end. Okay, so the way we solve this is we want A minus lambda, the determinant of A minus lambda I equals 0. So that just puts a minus lambda along this main diagonal. And then we do the determinant. So multiply minus multiply. And we get a minus times a minus, we get a plus there. So I had to get my calculator out and clean this up. But once you get it cleaned up, it's nice and pretty. So here's our characteristic polynomial. We get these two eigenvalues. Now we got to find the eigenvectors that go with them. So for lambda equals 4, I called this k sub 4 there. We want a minus lambda I times k 4 here, I guess, equals the 0 vector. So what that means is we take our original, we do this, only we have a matrix instead of a determinant. We plug in that lambda value. So I went negative 212 minus 4 and 214 minus 4. Subtract 4 along the main diagonal times this vector equals 0, 0. So then going across the top, we'll get negative 216 minus 126 multiplied by this vector. That gives us this equation. And then across the bottom, this vector, or this row times this column, 360k1, 210k2 equals 0. I chose to use the second one because it looked like it would be easier to reduce. So move this guy over, and then I divided both sides by 10, and then I realized I could keep going. I divided again by 3, so I guess I divided both sides by 30. You get here, and then the easiest way to make this equation true is just swap coefficients. Make him 7 and him negative 12. I could put the negative on either one. Doesn't matter where you put that negative. So you may end up with a more complicated eigenvector here. Any multiple of an eigenvector is still an eigenvector. Same thing with lambda equals negative 2. I think I used the top equation this time. And again, that reduced. And then I realized once I got here, I could reduce that even further. 3, negative 5. And again, any multiple of an eigenvector is still an eigenvector. Maybe you have the negative on top. Maybe you have 10 times this. It's still an eigenvector. So then our general solution is always going to be the x vector equals C1 times the first eigenvector e to the first eigenvalue t, C2, second eigenvector e to the second eigenvalue t. Now we do our initial conditions. X1 is just everything on top. So that's 7 C1 e to the 4t plus 3 C2 e to the negative 2t. X2, just everything along the bottom. So plugging in our initial conditions, plugging in 0, e to the 0 is just 1. We get this equation on top because we're supposed to equal negative 21, this equation on the bottom. Now we could just solve this by hand, but the student that asked me to look at this had tried this in the calculator, so I went ahead and did use the calculator to do this. So we would write this in the augmented matrix form. We'd write our coefficient square matrix here, put in our dashed lines, and then our coefficient matrix over here. We type that in the calculator. This is in the other order. Here it is typed in the calculator. Then I do row reduced echelon form on that matrix. It spits out this. So this says C1 is negative 3, C2 is 0. So, just going back up here, negative 3 there, 0 there. 0 times anything is 0. So all this stuff just disappears. This is our solution.